Hello, and thank you for joining us. Welcome to this presentation, which is part of an ongoing Goose webinar series exploring aspects of global sustained ocean observing. I'm Albert Fisher. I'm the director of the Global Ocean Observing System Office based here at the IOC in Paris. And for the next hour, we'll start with an approximately 30-minute presentation on evolving the tropical Pacific backbone observing system by Susan Wijffels. And this is work that was done by a team as part of the Tropical Pacific Observing System in 2020, a Goose development project. Susan's a senior scientist at the Woods Hole Oceanographic Institution in the USA and co-chair of the Argus steering team, as well as co-chair of the TPOS2020 backbone task team. After the presentation, we'll conduct a question and answer session using the question window. You can please ask your questions by clicking on the send to all button so that everyone can see your questions. And I'll moderate and select the questions and ask them verbally. The question window is already open, so you can start asking clarifying questions during the presentation. We're recording the session, and the link to the recording will be on the Goose website as well as on our YouTube channel, where you can find all the old webinars as well. Susan, over to you for the presentation.
Okay, thanks very much, Albert. So I am going to talk about the progress that the TPOS 2020 project has made since the first report came out several years ago. And I'm going to really much just focus on one aspect of the project, which is the recommendations for changing the Tropical Pacific Backbone Observing System. And the details around this will come out in the second report, which has gone through a review and will be out soon. The first draft of that is still available, and I'll show you where you can look at that link at the end. I very much want to stress that this is a huge team effort. There are many TPOS committees and task teams, and they have all made contributions not only to their specialist areas, but to what's been going on with the backbone. And so you can see these are the sort of lead authors and contributing lead authors for the report, but there are actually many, many others that have contributed to this effort. So the outline of the talk will be as follows. I'm going to talk a bit about what is driving the backbone design. These drivers were given to the task teams by our steering committee and our resource forum, which are the agencies that actually implement the backbone. I'll talk about where we got the backbone to in the first report, discuss a bit some of the new considerations since that report, and then look a little more in detail at the recommendations for the backbone as it is formed now in the second report. And there's a link there to the first draft, and it will be replaced by a more final version soon, probably in the next week. So when we started this several years ago, we were asked to think about the backbone in terms of 5 different functions, and I've listed them here. The first one really is to support and evaluate and validate ENSO prediction. So ENSO remains one of the key phenomena, not the only one, but one of the key phenomena that the backbone is there to look at. And so for ENSO prediction, but also other forecasting systems. And we know that there, besides weather forecasting, there's seasonal to sub-seasonal forecasting happening now, and also very new and fast developing field of coupled data assimilation for numerical weather prediction. We need to provide observations to quantify the evolving state of both the surface and subsurface ocean. We were tasked very clearly to think about the backbone as an integrated system between satellite-based sensors and in situ approaches. And so both satellite and in situ approaches must support each other because they are both actually equally important, I would say, in what we're trying to do. Another key aspect that the backbone must do is help advance understanding and modeling of the system. And this really is about observing phenomena and providing a infrastructure in which we can embed process studies. And then the last and very vital component is to maintain and extend as we can, or improve as we can, the tropical Pacific climate record. And so in summary, another way of putting that is that, we need an integrated backbone. It should enable better forecasts. It should track the state of the coupled system. We want to improve the climate record and increase our understanding of critical phenomena. And some of those critical phenomena are things like the near-surface physics on sub-daily timescales. So this is targeting things like the diurnal cycle, which we now understand is a very essential thing to understand AC interaction, things that are happening at fronts, and the very special physics near the equator. In our approach to trying to think about evolving the design of the backbone, our general idea was that elements of this network that addressed several of these functions were given a higher priority than elements of the network that might only address one. And it's that sort of simple framework that has guided some of the deliberations. So in the first report, which came out in December 2016, we had what we would call a fuzzy map designed. At that time, we had already come to the conclusion that the tropical mode array could be reconfigured, and it could be reconfigured to target key regimes and key phenomena, and to target near surface and short timescales. And this reflects what we believe is one of the unique capabilities of our MORD system, which is to capture that very fast physics between the surface atmosphere and the upper ocean. We also concluded that we could recommend to enhance Argo in the 10 north, 10 south band to increase both the subsurface spatial and vertical resolution, and again to better resolve things like fronts and mixed layer structures. We also worried about and thought a lot about our ability to estimate winds, and in particular we see the huge potential in improving our wind estimation, particularly through vector wind sampling from space, and particularly if we can improve the sampling within a day so that there's just better coverage, and in particular if that coverage is more smoothly spread through the diurnal cycle to avoid any sort of aliasing. And we still need to work on probing how we can better estimate wind in rainy regions. And we also recognize the very important role that subsurface salinity plays and advocate strongly for a follow-on mission, at the same time as maintaining some of our other key satellite measuring networks for sea surface temperature, sea surface height anomaly, and ocean color. All of those networks have critical in situ support systems such as surface drifters, sea level gauges, and so forth. Those are all things that we still require into the future. So since then, there's been a lot of work on many different aspects and many different groups engaged with the project. First up, the Biogeochemical Community, led by the TPOS task team, worked on their requirements and thinking for the science questions that they feel are the most important to address and the operational needs. And there's an entire chapter in this report dedicated to that. The TPOS Resource Forum has worked to secure support from existing partners, which is the US and Japan, and have successfully trained new nations into the discussion, in particular China and Korea. There was a deep consultation with the seasonal to sub-seasonal prediction community and the coupled data simulation community, both through surveys and some workshops. We also had interactions with and feedback from the climate research community, in particular the Clyde Pacific panel, who had great concern, as we do, about the climate record. Several technology pilots were funded and are underway, and we have early results from those. And because of this vexed problem of how to improve wind estimation, we have established a wind working group, which is working away at some of the details of wind estimation from both space and from in situ platforms. And the result of some of this discussion is, compared to where we landed at the end of the first report, is that we agreed that retaining a gridding capability in the tropical moored array is a sensible thing to do, to make sure in particular that we can capture decadal and centennial type variability. It confirmed our focus on this fast upper ocean coupling in physics and our focus on trying to expand the regimes that we sampled. It continued to confirm the need for better gridded products, particularly for fluxes and winds, and made us think about the observations we need to support this. As I said, it includes very specific biogeochemical enhancements. And I think the report identifies some key challenges and potential actions for the modelling and data assimilation teams, and there's an entire chapter about that. So let's revisit, well, we'll go through our thoughts on how to revisit the role of the tropical moored array. When the tropical moored array was first being rolled out in the late 80s and early 90s, it was almost alone in measuring the ocean. There were experimental, there was some sea surface temperature from space, but probably from an in situ point of view, beside the sea level network, there was no other system in place. And so its role then was really to operate as a broad scale real-time observing system. Now that is not the situation anymore. We have many sensors in space and other networks in place. And so we thought hard about the role of the tropical moored array and thought about what do they uniquely contribute to the observing system. And one of the things they do, which we have no other technology to do, is to deliver very high frequency, hourly or better, co-located ocean and surface observations at a specific site. No other observing system currently can do this besides a moored ship. And so, that is a very powerful thing and in much demand by many of our user groups. But in the meantime, satellite-based flux estimates have evolved hugely, particularly for wind, and I'll talk a bit about and show you some examples of that. In the current TMA, as you can see, I don't know if I can get my mouse working, I probably can't. The amount of surface velocity data that we get is highly limited to 3 sites at the moment. And another major limitation of the current tropical moored arrays, even though it does deliver sensible and latent heat fluxes from many sites, it only resolves the radiation fluxes and rainfall at a much smaller number of sites. And currently there are only 4 sites operating where we can fully estimate the total heat and freshwater fluxes. And a major demand from many of our users is to be able to directly measure fluxes in the total fluxes in more places. And the other limiting factor of the current configuration is that the ability to measure the mixed layer depth and is very, very poor. And I'll show you why that is in a minute. The coverage of biogeochemical parameters is weak. PCO2 is one that is measured currently in the past along the servicing lines. Those are the green lines, and only a few sites along the equator where PCO2 is being measured. So that's pretty limited sampling. I just want to stop a little bit and talk a bit about, I think, what's been one of the major revolutions in wind estimation, which is the ability to measure vector winds from space using scatterometers. This is an example of a westerly wind burst in the Western Pacific in 2015. The white vectors are from a scatterometer product, largely based on the ASCAT missions. And the pink lines there are a view of the same wind burst from the tropical mold array. And so you can see that there's a huge amount of structure and curl, wind stress curl, which is essential for, essential part of understanding what drives the ocean dynamics, that you can only get a hint of from the mold array, and that the scatterometers capture very beautifully. But the scatterometers are also limited. They're not perfect by any means. And so it's really a combination of these things that we need to get a better view of the system. Here is another example of a wind burst. And again, you can see these small curl events north and south of the equator, and lulls in the wind field that are only hinted at in the mold array. This is a 3-day average. And I guess what we see in this plot here is a time series at 2 north and 165 east, showing those two wind bursts. And so the first wind burst is this positive peak here, and the second wind burst is here. The green line is the 3-day average from the scatterometer, and the black line is the record from the buoy. And so you can immediately see that at the low frequencies, they agree fairly well, but the buoy is capturing all of the high frequency variability associated with convection and other really important variability for the fluxes that scatterometers simply cannot see. And so really it's this combination of technologies that we need to get the full picture. And so we hope to exploit this in the new design. If we look at the ability of if we look over a longer time period, and here we have an analysis from 2007 to present, the vector wind products work very well for weekly timescales and longer. And this is just a plot. On the left is for the zonal wind of the percentage of variance captured at the sites of the moorings that we've had in the past. And over most of the sites, we can get up to 90 to 100% of the variance of the wind captured from space for the zonal wind and for the meridional wind. Where the wind is strong, we can capture it very well. Where we don't do so well is where the wind is weak, and this is a known thing. And there are also issues with the scatterometers in rainy areas as well. And so some of these issues, these differences in how we estimate wind from space or from a buoy are being pursued by the wind team. And so there are details of some of these things that we feel are worthy of advancement and might guide what in situ observations we need to better exploit the scatterometry and how we can build much better gridded products. So getting back now to how we feel we should reconfigure the mold array, what we advocate is to redesign the baseline tropical mooring. So on our left here, so what we're saying is we want to get more value out of the moored sites, and we advocate a tiered set of parameter suites for the buoys. So the first tier 1 in the new TPOS will be quite different from the existing TOW or Triton. So the existing TOW here is on the left. Here is the Triton buoys as they are currently operated. They have fairly sparse temperature at the subsurface, and they measure wind, air temperature, and humidity. And the Triton measures precipitation, pressure, and shortwave. And again, it has more salinity measurements, but also fairly sparse. In the tier 1 of the TPOS moorings, and this is what we call our baseline mooring, which will be, we advocate be rolled out at every site in the new TMA. It will have much higher vertical resolution in the mix layer, allowing us to track mix layer depth much more closely. It will measure near surface current, and it will include all the variables required to calculate the full heat flux. And so that will be a mooring where we can do the full fluxes, we can track the mix layer depth, and we get near surface velocity on hourly or better timescales. A Tier 2 version of this will be additionally equipped with upward-looking ADCP or some other technology in order for us to get shear in the mixed layer. We believe that measuring shear in measuring the ocean shear in some of the key regimes will drive a lot of insight into the fast coupling of the atmosphere and the ocean. And exactly where these Tier 2 moorings are deployed is still a work in progress. But for the Tier 1 moorings, we advocate these become the standard TPOS mooring. If we think about where we want to deploy these moorings, one of the things we looked at was the climate record, in the sense of where are the existing moored sites most contiguous and go back further in time. And so there are some meridional lines where the coverage is very, goes back over 30 years and is quite complete. And there are other areas where this isn't true. So that was one of the things that we looked at to try and understand which sites we might want to prioritize. So in this figure on the left is the number of years that the site's been since the site was established, and on the right is the percentage of coverage of data return. We can do the same thing for latent heat flux, which has the components of which are measured at each mooring. This is much harder to do because besides wind, you need air temperature and relative humidity and sea surface temperature. So there are many more variables that need to be complete in order to capture that. And so you can see there are certain lines where we have longer records than others. The other concept that has been driving our thinking is the idea that where we measure this vast upper ocean physics is going to be guided by the kinds of regimes that exist in the area. And the existing TPOS has largely been within plus or minus 8 degrees, sorry. And so there have been requests, and we are trying to feed those to sample into the dry inflows, into the convergence zones. So the tropical convergence zones are these blue streaks here where it's cloudy and low evaporation. And so we are advocating to put sites into these dry inflow areas for the convergence zones, and also to sample more into the South Pacific convergence zone and further north into the West Pacific warm pool. Because of the special stratification that happens in high rainfall areas, and also the complexities of wind estimation from space in convective and rainy regions, we have also tried to look at where the really most extreme rainfall happens and when it happens. And one of the seasons is in July, when the ITCZ is a little further north than normal, and so we're trying to target new moorings that capture those very high rainfall seasons in July and October, and again trying to increase our sampling in the South Pacific convergence zone. There was also a lot of work done by the task team focused on the biogeochemical responses in the tropical Pacific. And here we have those illustrated by composites for an El Nino year and a La Nina year. And so the scales that you see here have been giving guidance to their requirements of where we sample biogeochemical parameters. So this is our proposed sketch, more detailed sketch of the new BackBone. And so, as I said, it's an integrated system. So the satellite missions are equally important and vital to this effort. And there are specific recommendations about some of those, particularly sea surface salinity and the vector wind sampling. This is the existing tropical mortar ray in the top panel, and then below that is the proposed new configuration of the mortar ray. And so all of these sites, both the green squares there, they are the sites that existing sites that we will retain. The green dots are new sites that we hope to establish. And then you can see there are some off-equatorial sites here that we suggest a lower priority. And so this, and then in addition, there is a large extension of moorings in the Northwest Pacific that are supported by both JAMSTEC and our Chinese partners. The purple ones are the proposed ding array, which is looking at focusing on processes in the warm pool and further north. Part of this design is to also focus on the equatorial physics with a call for increased velocity sampling at 140 west, as well as, and this is subsurface velocity, as well as retaining subsurface velocity along the existing sites that now have been operating for decades. These records are highly valued by many communities, particularly for validation of models, and we advocate to continue those. In fact, the equatorial sampling in the new TMA is retained and enhanced in this new design. And as I mentioned, we are looking for a poleward extension along certain meridians. In addition, we are advocating and continue to advocate for a doubling of the Argo background sampling within plus or minus 10 degrees, and have added the BGC mission to begin tracking the subsurface return of key biogeochemical parameters such as nitrate, oxygen, chlorophyll, and pH, and some of the optical parameters. There are many other elements of the observing system that we have considered and we believe remain essential to many elements of the TPOS. These include the surface drifter networks, the XBT network, the GoShip network, which is one of the few ways of tracking the deep subsurface in the tropical Pacific, the volunteer ship network, and the sea level network. If we now go back to for surface parameters and compare what we might expect across some example parameters, we can look at this view. So on the left is the present returns from the system as we have it, and on the right is what we expect from TPOS 2020. And so for winds, we can see that the grid in the central and eastern Pacific expands poleward but thins out a bit in the off-equatorial region. For 4 meter for surface currents and winds, you can see that our collection of surface current is going to greatly expand, and this is to feed into many different areas of science. And you can look at those in the report. The number of sites where we're returning total heat fluxes is going to expand greatly, and to make it possible to start actually looking at heat fluxes, not just total heat fluxes across a huge number of regimes, but actually to contemplate looking at the large-scale, mapping the large-scale fields directly from the mortar ray. And for CO2, there's a small expansion of the PCO2 sites, retaining the ones that exist, and advocating for shipboard measurements of PCO2 during the servicing voyages. One of the exciting pilots underway is pilots for our Tier 2 type concept, which is to measure shear in the upper part of the ocean. And these are just 2 examples of diurnal composites from those pilots. One here is from the ITCZ location here, and that's in the bottom panel. And so this is looking at shear relative to wind. And you can see this very shallow shear layer here. And so, but you see a weaker diurnal cycle at this site compared to at the warm pool front on the equator at 155 west, where we can see a very different characteristic of the upper ocean shear. And so this is just a little insight into the kind of information that we can get if we can augment a few key moorings with this Tier 2 capability. Another key question that we have thought very hard about in reconfiguring the moored array, and in particular possibly decommissioning some of these off-equatorial sites, is will we be able to track large-scale decadal and longer shifts in surface fluxes, such as the wind fluxes. And I feel that we probably can, and the reason for that is that these wind shifts tend to be of very large scale. And here's one example from de Boissesson et al., where they measured a wind shift using scatterometry, and it was between the 1990s and the 2000s. And so you can see the footprint of that wind shift, which is a strengthening of the trade winds. And if you just sample that wind shift, which you can see the structure there, from the existing moored array and linearly interpolate between the moorings, so this is an estimate here, you can see that you can, and then you look at the error you get from subsampling this pattern with the moorings. You can see you get fairly good ability to recover the pattern. But if you do the same thing with the new TPOS design, you do almost as well as in recovering this pattern. And so our feeling is that we haven't lost a lot as far as our ability to track these very large-scale wind shifts. That this is one example of them. And here on the left, you can see over plus or minus 10 degrees, both moored arrays do almost as well. We can do a similar exercise based on an estimate of a decadal trend in latent heat flux. So here's one estimate of a trend in latent heat flux based upon a satellite product. We can do an interpolation from the existing moored array and the new moored array, and they perform almost equally well as far as recovering, having relatively small error within the domain of the moored array for recovering this pattern. In the subsurface, we can see that we can have another view of what the present looks like and the proposed TPOS looks like on the right. So for velocity, we propose to retain the existing subsurface velocity measuring sites, and they will be augmented by 2 sites in the Northwest Pacific, and in particular a transport resolving array at 140 West, which I'll show you in a minute. For subsurface temperature, we shall thin out the moored array, but Argo will be doubled, and I'll show you some evidence of how we feel that subsurface variability will remain well captured. Similarly for salinity, very few moorings currently measure salinity. We have background Argo. By increasing the Argo density, salinity estimation in the subsurface will increase a great deal. And then for biogeochemical measurement, it will truly, if we can implement the BGC Argo sampling, it will truly revolutionize our ability to monitor those fields. I see I'm running late, so I'm going to speed up a bit. The transport array that we advocate for at 140 West will deliver for the first time, I think, true estimates of a time series of EUC transport instead of just the core velocity. And this is called for in many studies on decadal dynamics. This is an example here of the mean field based on synoptic ADCP measurements, and you can see the proposed moored sites there. And so we're confident that this set of moorings will do quite a good job of capturing that current system. In the subsurface, studies have been performed to quantify what we feel will be the losses and gains in subsurface estimation. And if we just concentrate, say, at the middle panels here, this is at the 10-day timescale. This is an estimate of what we think the mapping error is with the current system. And so you can see low mapping errors at the current Maud array sites. And this is with the current Maud array and regular Argo, and then quite high errors in between. When we double Argo and reconfigure the Maud array, overall you can see the errors drop. It becomes much bluer, except right along the Maud sites. And so here is the difference between the new map, the TPOS map, and the current observing system. And we gain nearly everywhere, that's blue, so we beat down the error nearly everywhere, except right at the locations of the sites that we believe are lower priority. I'm going to skip through this. We have done other data assimilation studies. This is work by Laurent Gaston and colleagues, again confirming that with altimetry and doubling Argo, we will advance greatly subsurface state estimation. And so we have a much more specific set of recommendations now for the new BackBone than we did at the end of the second report. And I feel a better understanding of what the community is looking for. And discussions are now underway to think about the implementation of this. I'm not going to go through this complicated diagram in detail. It is in the report. But you can see at the top there are years and different elements of the array. And you can see some of them will likely take up to 5 to 6 years to implement. And some are already underway. Little P symbol here are for pilot phases. And the double bars here are for assessments. And the assessments and pilot part of this implementation are crucial. And it's part of what we think about as a staged implementation, where the assessments of the changes are crucial to help us learn about what we're doing better, where we're not meeting expectations. And trying to build strong community participation into these assessments, I think, will be important. And as I mentioned, the transition will take many years. So in summary, we think that through this very vigorous discussion that we've been having amongst many people called the TPOS2020 project, we're already delivering new gains because it has invigorated agency interest and is in training new partners. The second report will soon be published with many more details than I could have covered today. It contains specific details on the BackBone, but also many chapters on regional process studies and pilot studies. And a key chapter that I recommend you read is about the work with the modeling teams. And TPOS is recommending a much more regular and structured model intercomparison exercise to deal with some of the very tough issues such as model bias. Comment and feedback is still very welcome. And we're not quite done with the project. We have one final report to deliver, and so we really encourage folks to read the reports or sections that they might be interested in, continue to give us feedback. And I'll stop there. Thanks very much.
Thank you, Susan. That was a really great presentation. I really appreciate it. A lot of considered recommendations, and really clearly a lot of work by the teams that you've been working with. So the questions are open. We have one question that's been asked already, but I encourage all of you who are online to ask questions in the question window and click on the Send to All button. And let me start with a couple of questions of my own. Just looking at the in situ observations, is the cost for what you're recommending higher, lower, the same compared to the present set of observations? And did you have any guidance on that from the funders and the sponsors of the TPOS2020 project?
So the cost is definitely much higher because we are asking both in the Maud array and in Argo for an increased investment. Did we get specific guidance? Not really, but I would say that during the project there was constant briefing of the agencies that are interested in supporting this effort to give us some feedback. I would say, you know, as a rule of thumb, and this was sort of in my mind, that we should ask for more, but maybe not double. So somewhere in between. I don't quite know where we've landed. One of the issues we face is that part of the investment is equipment, part of the investment is salary, part of the investment is ship time, and how those costs are paid for and covered is very different from country to country.
Yeah, you mentioned that the project has trained some other countries and China in particular, and do you hope that there'll be more investment from a larger set of countries around the Pacific?
We very much hope so. And so, on the resource forum and also the steering committee, there is a larger group of countries involved, but not all of them have stepped up to contribute. And so I think it's, the more investment we get by more countries, the more that we can do, and probably the more of the existing infrastructure we can, even retain. So, yes, we still need more countries to contribute. I would say the reliance on the US investment is still, even for Argo, is too skewed to be comfortable.
Okay, so diving a little bit more into the contents of the report, you showed quite a series of evaluations of how patterns or different phenomena can be captured with the present and the future design with a mapping error approach. So two questions about that. Is that something that could have been done through using model outputs and with observing system simulation experiments? Was that considered?
Okay, I'll take that one first. So one of the studies by Laurent Gaston is indeed using what we call an OSSI, which is they use a nature run of a model, sample it with the existing Maud array and sample it with the existing Argo array, and then go back and sample it with the TPOS enhancements, and then put that information into a data assimilation system. And what that study shows is actually, for temperature in particular, the existing Argo system with altimetry and sea surface temperature from space are already incredibly powerful at state estimation. But for salinity, the enhancements we get from doubling Argo, particularly at higher frequencies, and are quite large gains. And so, but that is just from one system, and we would love to see more of those studies done. But they're substantial. There's a substantial amount of work to do. But if other groups want to take that on, we'd be really keen to talk to them and work with them on that.
You mentioned that a good part of the second report is about the modeling systems and some of the remaining and stubborn biases in the model systems. Does that hamper an approach of using models to do this kind of work?
Yes. So one of the worries that we have, and I think our modeling teams sort of agree with us, is that the model bias makes the models tend to drift away from the initial states rather quickly because of biases in the physics that we have not yet really been able to get rid of. And so it's problematic when you're ingesting observations, and most of the increment of that observation is to correct the model bias rather than to initialize a dynamical anomaly. And I think for many of our systems, we're still in the situation where the model bias is as large as the signal that we're trying to initialize. And so I think that remains a big challenge, both for prediction systems, but also when we try and use these models to give insight into the value of the observing system.
In your answer, you just mentioned one of the benefits of increasing Argo was capturing the salinity signal, but we have a question from Lucia Upchurch. More generally, could you speak to the benefits of increasing Argo? What do you expect to gain? And what are the prospects for greater investment across many Argo partners?
So I think what Argo can do very well is it has very fine vertical resolution. And so our ability to capture the fine details of the hydrography is it's a single sensor that is profiling, and so the details of the hydrography and, say, being able to track barrier layer changes and mixed layer changes is high. By increasing the Argo density, we feel that we can track fronts better, and we can also increase in general, the spatial resolution of the salinity estimation. So those are some of the largest gains that we're going to get from Argo. The prospects of increasing having the Argo partners come to the table, I think that remains to be seen. Argo is going now through a design change itself and is contemplating a new global mission, which will expand into the polar oceans, into the deep ocean, and these tropical enhancements, as called out by TPOS2020, is one of those enhancements. The other major enhancement will be a global VGC mission for Argo. So I'm hoping that that global change in Argo will also include the resources to double Argo in the tropical belt. But I do think for many, for some agencies, it's a high priority.
You showed some work where the backbone array is going to be expanded to the north and to the south, particularly to the northwest, and targeting some of the inflow regions for the convergence, some of the high rainfall areas. Is there science that might guide us as to whether these zones will actually stay put with climate change?
I don't know if there's been a lot to look at those zones or how far they would move. They already seasonally move quite a bit, and so I anticipate that the sites that we're advocating for now will sample those zones, for certain seasons. But I would say probably for the lifetime of this array, which might be, the next 20 years, I don't expect those zones to move radically out of reach of the Maud array. But I can't point to a study that shows that.
Okay. Let me turn to some of the new work since the first report, which is the biogeochemical requirements and the biogeochemical work. How are the requirements integrated into the work of the backbone team? Did they just build off the backbone as a given, or was there some more integration of the work of the biogeochemical test team?
Functionally, the way we did it was that the co-chairs of that task team often joined the backbone discussions, and certainly any face-to-face meetings that we had. So we didn't interact with the entire biogeochemical task team, but we certainly interacted a great deal with the two co-chairs who were funneling the advice of that team into the backbone. Yeah.
Okay. And let's see, so you mentioned some of the key phenomena that guided this work, heat fluxes in the Diurnal cycle, the upwelling regions, rainfall, shallow mixed layer depth, decadal change and centennial change as well. Did you think about the sort of key applications that drove the work as well? Is there a real focus on seasonal forecasting, or was there a broader set of applications you were thinking about in developing the backbone?
Yeah. So seasonal forecasting was, I would say, one of the key application areas. But as I mentioned, we did talk to the seasonal to sub-seasonal forecasting community, and also the very new kind of coupled numerical weather prediction community, which is developing very quickly. And while those communities couldn't give us specific requirements around what they need to initialize their forecast, because I think it's too early days, they did give us some insight into the phenomena that they believed they were most interested in, and that is reflected in our investment in our trying to understand the fast physics, the coupling between the ocean mixed layer and the surface atmosphere. So we have talked to right across, we have talked to not just the seasonal forecasting teams, but also sub-seasonal, and coupled data assimilation.
Now you focused on the in situ elements, even though you took the satellite observations strongly into consideration. Do you think there's requirements for in situ meteorological measurements other than those that are taken at the surface from the moorings that would have, was that a consideration? Was there a team looking at the meteorological side?
We have in TPOS a planetary boundary layer team, but there are several atmospheric, I would say more true atmospheric scientists involved in the project who did also bring up that point. And so, but it hasn't been a major driver of the project so far. One of the concepts I didn't talk about much because it's largely still conceptual is well, there's two concepts. One is of supersites. And these supersites, besides measuring much more detailed information using, say, moorings, might also involve things like LIDARs and atmospheric sounding abilities, either on an island or on a buoy. And so there is some discussion now about these supersites, how they could be used, what problems they would solve, and would they be part of the backbone? Should they be in a fixed location or be moved in a campaign mode from regime to regime? So, so yes, but you know, we are. So I would say that we haven't looked a great deal at the atmospheric part of the observing system. We have mostly focused on the surface meteorology and the ocean today.
We have a question from Tosta Tanoa, which says that I did not see any new platforms mentioned. For example, sail drones, wave riders, and subsurface gliders. Were these considered as potentially part of the design of the backbone? And he makes a note that particularly autonomous surface vehicles can be powerful for certain observations, for example, PCO2 measurements. Yes,
so there is a whole section in the report about pilots and consideration in detail of many of these new technologies and an assessment of their readiness level for the backbone. So, you know, here we are focusing on things that we believe can start to go in the water next year and the year after and be operated probably for the next 10 or 15 years. I'm not, you know, there are many pilots going on with some of those technologies. And they might become part of the backbone over the next 5 to 10 years, but we didn't feel any of them were clearly ready to start next year, for instance. So we have focused on pretty, you know, technologies that are what we believe to be very, very well road tested and have a high readiness level. Not to say that we're not excited about those new platforms, and surely in the future they will be part of the backbone.
So I guess I have a question about the time scale of the backbone. You mentioned something like 20 years. You also mentioned the tremendous effort of the community in working and developing the reports of TPOS 2020 project. How often do you think this kind of exercise will need to be repeated for the tropical?
Wow. Yeah, that's a tough question, Albert. I'm not sure I'm the wisest person to answer. Yeah. I mean, really, it's our funding agencies that will trigger these reviews. And I don't think there's a clear-cut answer. There's a practical answer in that it just takes a certain amount of time to establish things, to get countries to intercompare their technology, have uniform, you know, achieve uniform accuracies and agree on ways to measure things and calibration and all of that, which is incredibly important work to produce useful, particularly a climate record. And so you can't be changing it every 5 years. And technology evolves very quickly, as Tosta's question triggered. So, I mean, my experience is maybe every 10 or 20 years is about right. Maybe every 10 years for a review, just to look back at how well we've done and to look at new candidate technologies and what role they could
We have a question from Antonietta Capotondi. Sorry, I don't pronounce that properly. And it reflects some of the concerns that had also been raised by the CLIVAR Pacific panel, and particularly criticism of the recommendation to discontinue some of the moored observations. Antonietta asks, given the uncertainty in how the tropical Pacific climate is going to evolve, it seems like it would be wiser to keep and augment the current mooring configuration. Could you explain why we need to remove some of the town moorings?
I think we basically think that the data that they collect can be largely recovered using other technologies. And so we agonized over this since the very beginning of the project. But we believe that the decision we've come to is that many of the measurements that we can make with those moorings can be replaced by a combination of other networks, and particularly some for the surface fluxes from the satellite networks. And that the expansions, to deliver fluxes, to expand poleward into new regimes are more valuable than retaining some what we think of in the factors of redundancy in the system. And in fact, for the very long time scales, the interpolations that we've done, and we've really, as I said, agonized over this, is that we can recover those large-scale changes with the new design. And so we know that not everyone agrees with that, but there are many ways to build a climate record, and I personally feel quite comfortable that for these decadal and longer-term changes, this integrated system will perform very well.
Okay, thanks, Susan. We have a specific question from Andre Belem. A question about verifying the bulk parameterization and the impact on the latent heat flux, I think, the LHF. Is there any particular work, you mentioned the super sites around that, is that an objective of the work looking at the air sea fluxes?
Yes, so that would be one of the potential problems that we could look at with a super site, because we would be able to have direct eddy correlation flux systems on those sites, and to be measuring the latent heat and the sensible heat directly, rather than inferring them from bulk formula. This is already starting to happen in many different regimes globally, but a supersite in the tropics, looking at the peculiar regimes of the tropical Pacific, that would definitely be one of the targets amongst many others. Yeah.
Thanks. And actually, the very first question we got from Mateus Paiva is a specific question about, is there any possibility of expanding this type of observing system to the other oceans like the Atlantic? Maybe let me generalize the question actually a little bit. It has been a lot of work. What lessons have you learned from the review process of TPOS that you could give to groups that are looking at the tropical Pacific or the tropical Indian observing systems?
I don't know if I feel wise enough. I guess, I suppose what I enjoyed most in this discussion was having the different task teams coming with different points of view, and from different regions too. I suppose what I found different about this particular exercise and any previous kind of observing system review that I've been involved in is this idea of looking at multiple uses of the infrastructure and grading the value of the infrastructure by their ability to deliver to not just one thing, not just research or not just this problem or that problem, but multiple things. So that's a litmus test for the value of that infrastructure. And also looking at it really closely of how satellite data streams and in situ data streams support each other to give the community what it needs. Most, for example, much of the research done in climate dynamics do not use the direct observations, they use gridded products. And so another big lesson here is to try and understand how the gridded products are made, what the different observing systems contribute to that and how we can improve that. And so that's also been a really fascinating journey here in the TPOS project.
Okay, thank you very much for that, Susan. We've come to the end of the hour, actually, so we've run out of time. I want to thank you again, Susan. Thank you, the audience members who stayed on with us. Again, this webinar will be recorded, put on YouTube, on the website, and look also on the website for announcements for future webinars. Thank you again, Susan.
Thanks, Albert. Bye.
Bye-bye.